Hello everyone. So we are going to start the part 3 from the chapter Rheology. So in this unit we are going to discuss regarding the types of the fluid. Generally the fluid are divided into two types, the Newtonian types of the fluid and the non-Newtonian type of the fluid. So without wasting any time, let's start. So before going into the types of the fluid, let's have some background. See, the Newton's law of flow. So what does the Newton's law of flow states? So the thing is that Newton, he was the first scientist to study the properties of a liquid in a quantitative way regarding the forces applied over the fluid, the stress and the shear shown by the fluid, the strain that is achieved by the fluid, right? So the Newton's law of flow, actually it states that the shear stress between adjacent fluid layer, if we give a shear stress between adjacent fluid layer, if we just recapitulate the concept we have studied in the flow of fluids in the pharmaceutical engineering, we know that the fluid, they always flow in layers, right? The lowest layer, they always have the highest viscosity, as because it was in or it is in touch with the surface via which it is flowing, and the middle layer, if we consider a pipe, the middle layer, it having the highest velocity, right? So now you see the shear stress between adjacent layer of the fluid, means the fluid, they are flowing in layers, right? So the stress between the adjacent layer, it is proportional to the velocity gradient. It is proportional to the velocity gradient between the two layers, or you can say shear rate, means the stress, the shear stress between the two layer, it is directly proportional to the shear rate. That is the concept Newton has come up with. Okay, now while studying this model, Newton has introduced a model, or while studying this particular concept, he has introduced a model. This model, it was known as the two-plate model. In the two-plate model, nothing is there. Suppose this is one plate, just this is the upper layer of the plate and this is the lower layer of the plate. This is a two-plate model, right? In between this there are fluid, right? In between these two plate, this is the upper plate, this is the lower plate. In between these two plate, there are fluids which are divided in layers. Suppose this is the lowest layer, above which one more layer is there, one more layer is there, like that. So this is the upper plate, this is the lower plate. For your reference, I have shown you. So the two-plate model, it provides a mathematical description for the viscosity. Done. So mathematical description of viscosity means viscosity, we all know that viscosity, it is the lagging force towards the flow of a fluid, right? The viscosity, it always tries to lower the speed of or the flow of a fluid. Clear? So there are two plates with fluid placed in between. I have already shown you there are two plates. Suppose this is the top plate, this is the bottom plate. In between the fluid is present. So the lower plate here, the lower plate, it remains static. The lower plate, it remains static, it don't move. But the upper plate, it is moving from this direction to suppose this direction. The lower plate will be static, it will remain as it is, whereas the upper plate, it will be moving. So while moving, this plate will appear, or this plate will apply some sort of stress over the surface of the fluid here, right? Isn't it? As because it will move, right? This upper plate will move. This, while moving, this upper plate will introduce some sort of stress over the surface of the liquid which is in touch with the upper plate, right? So the upper plate, it drifts aside slowly. It will drift aside very slowly, right? And subjects the fluid to a stress. So when it will slowly move, the fluid attached to the upper plate, it will have some sort of stress, right, which is parallel to its surface. So this fluid was earlier parallel to the surface of the upper plate, right? So when the upper plate will slowly move, it will produce some sort of stress to the upper layer or upper layer of the fluid which is or which was in touch with the upper plate. So it is known as the shear stress. The force applied to the upper plate divided by the plate's area. Suppose the upper plate has applied a force, suppose 10 Newton, and divided by the area upon which it has applied the force, it defined as the shear stress. Means, what do you mean by shear stress? Force applied per unit area. Clear? So force per unit area, it results in this particular quantity, that is Newton per meter square, which is also known as the Pascal. So the unit of shear stress, it is the Pascal. Now you see, sorry, the two-plate models, it allows for calculating another parameter. This parameter, it is known as the shear rate. Shear rate, it is nothing but small d by small dv by small dr. The small change in the volume by small change in the distance, right? So the shear rate, it is the velocity. You can define the shear rate as, the shear rate can be defined from this experiment as the shear rate, it is the velocity of the upper plate. Velocity of the upper plate divided by the distance between the two plates. The velocity of the upper plate divided by the distance. Suppose this is the r, this is the r, this distance, it is the r. So shear rate can be defined as the velocity. Suppose velocity is v. So small change in the velocity divided by small change in the distance, or the distance between the two plates. That is its unit. The unit of the shear rate, it is the inverse, or you can say reciprocal of second. It is a reciprocal of second. You can write 1 by s or s inverse. Clear? Now the Newton's law of flow. What actually Newton's law of flow states? See, the rate of shear, it is directly proportional to the shear stress as per Newton law of flow. So this is the shear rate, this is the shear stress. As it is directly proportional, it will go in this 45 degree, right? So in another word, twice the force would move the fluid twice as fast. Means if we increase, or if we double the force, means double the force applying to a fluid, the velocity of the fluid will also increase to its double, as it is directly proportional, right? Example of Newtonian's liquid or fluid, it is castor oil. Castor oil is a very classic example of Newtonian fluid. So Newtonian fluid, they generally follow this shear rate. It is always directly proportional to the stress. Similarly for viscosity also, you see, they remain the parallel. Yeah. Now you see the flow, or the flow of any fluid can be divided into two types. Number one, it is the Newtonian. Number two, it is the non-Newtonian. So Newton's law of flow, actually Sir Isaac Newton was the first to express the basic law of viscometry, describing the flow behavior of an ideal liquid, right? So as per him, the F is equal to eta into G, where F is the force, eta is the viscosity, and G, it is the shear rate. So shear stress, right? The shear stress, it is directly, or you can say the shear stress, it is equal to viscosity into shear rate. I repeat, the shear stress, that is a force, it is equal to the viscosity of the fluid into the shear rate. Clear? Now there is a concept in the Newtonian flow. So this concept, it is known as the absolute, or you can say it's the dynamic viscosity. So what do you mean by dynamic viscosity? You see, dynamic viscosity, it can be defined simply as dynamic viscosity is the shear stress divided by the shear rate. Shear stress divided by the shear rate, that is the dynamic viscosity. So we all know that viscosity is equal to the shear stress divided by shear rate. Clear? This is the shear rate, nothing else. dV by dr we have already discussed, it is the shear rate. So dynamic viscosity, eta is equal to F by 8, it is the shear stress divided by shear rate, right? So the fundamental unit of viscosity is the poise. It is the unit of viscosity. Now the shear force required, this is the definition, okay? The shear force required to produce a velocity of 1 centimeter per second. The force required to produce a velocity of 1 centimeter per second between two parallel planes of liquid, each of 1 centimeter square in area, separated by 1 centimeter. That is the unit, or that is the simple definition. So fluidity. Now what do you mean by fluidity? Fluidity, it is simple. It is the reciprocal of viscosity. Viscosity, we know that what is viscosity. It is shown by the unit or by the symbol eta. So fluidity is equal to this phi is equal to 1 by eta. That is its unit. It is the inverse bias. The fluidity, it is just opposite to that of the viscosity. The viscosity, it hinders, it stops the flow, right? Whereas fluidity, it allows the flow. The next concept, it is the kinematic viscosity. So what do you mean by kinematic viscosity? So it is the absolute viscosity divided by the density of liquid at a specific temperature. I repeat, kinematic viscosity means it is the absolute viscosity divided by the density of liquid at that particular specified temperature in which we have carried out the experiment. So kinematic viscosity is equal to eta by rho, where rho, it is the density of the liquid at a specified temperature. So rho, it is the density of the liquid, and the unit of kinematic viscosity, it is stock, small s, stock or centi-stock, small c, small s. Clear? The next concept, it is the temperature dependent. We all know that with the change in the temperature, the viscosity changes, right? If we increase the temperature, the viscosity will come down, right? So basically, when the temperature increases, viscosity, it goes down, or viscosity, it decreases in a fluid. So the relationship between this temperature and viscosity is very simple. Eta, here eta is equal to a small e to the power ev by RT. So what are these terms? Eta, we know that this is the viscosity, AE, right? So simply the EV, it is the activation energy which is needed. It is the activation energy which is needed to increase or to initiate the flow of a static fluid. EV, it is the activation energy which is needed to initiate the flow. RT, we know that it is the natural gas constant, right, at a temperature T. And A, it is the constant depending. So A, it depends upon the molecular weight and molecular volume. The A, it is a constant, but it depends upon the molecular weight and molecular volume of that fluid, of which we are checking the change in the viscosity with that of the temperature. So thank you everyone. Hope you liked the video. If you liked the video, just press the like icon. You can share this video and you can subscribe to my channel. Thank you once again.